Welcome back to Math 130, Applied Algebra and Trigonometry. Today we'll be talking about logarithms of base 10. I would like to start by just playing around with the properties that we've talked about so far and with the action of switching from logarithmic form to exponential form. So here's an example. Let's look at the log base 10 of x equals 4. Okay, and I would like for us to solve for x. So looking at this, not really a way I can reduce that, do anything with it in the logarithmic form. Let's change it to exponential form. So here's my base, and I have been making the exponent green, so let's do that. The exponent is 4, and that is equal to the argument. So what is 10 to the 4th? Well, that's 1 with 4 zeros following it, and that is what x is equal to. And that was example 1. Let's do example 2. Okay, example 2, the log base 10 of 1/100th equals -2. The question is this true? Let's see if it makes sense in logarithmic or in exponential form. 10 to the -2 equals 1/100. So 10 to the -2, the negative drives the base to the denominator. You have the same exponent, only it is now positive. And is that equal to 1/100? Yes. 1/10 squared is 1/100. The answer to the question is yes, it is true. Okay, let's move this out of the way. For example 3, let's expand this expression. In other words, let's rewrite it as the sum, difference, and or multiple of logs. Okay, so if I rewrite it with my color coding in place, I have log base 10 of 1,000 x to the 4th. Okay, and that, of course, could be rewritten because 1,000 is definitely not prime. It has some factors, and it has factors of 10, in fact. Let's see, 1,000 is equal to 10 cubed. So that's 10 cubed times x to the 4th. So we have a product there. We do not have the same exponent on each of those factors of the product, so we can't apply the power rule yet. Instead, we have to apply the product rule first. So we have log base 10 of 10 cubed. The product rule says if there's a product inside of the log, then you re-express it as the sum of 2 logs. So log base 10 of x to the 4th is added to log base 10 of 10 cubed. Now that we have this set up where we just have a base and an exponent in each argument, we can now bring the powers of each of those arguments out front by applying the power rule. So if we pull those out, what we have is 3 log base 10 of 10 plus 4 log base 10 of x. Notice that we have the log base 10 of 10 here. So the log base 10 of 10 is 1. Therefore, that first term has become 3 times 1 plus 4 times the log base 10 of x, or 3 plus 4 log base 10 of x is the most expanded and evaluated form we can get to of our original expression. You may have noticed that every example I did had a base of 10, and that's because the log base 10 is a very special log. In fact, log base 10 is called the common log. It's quite common. So example A, the log, or the common log base 10 of 100 is 2. Please remember that when writing the common log, you do not have to write the 10. You can just write it like that, and it means the common log of 100 is 2. We've been working with some very useful techniques, but it's not always possible to evaluate very much of a given logarithmic expression without a calculator. So let's talk about how you do use a calculator to evaluate logarithms. So let's look at an example B. Let's take the common log of 352. All right? That's not something that we can really work with using the properties of logs and everything. This is something that needs to go straight to the calculator. Here's a sequence of keys that you can press on your calculator that will give you the log base 10 of 352, or the common log of 352. On your screen, it will look like this. At that point, if you have it set as I do to give you the exact answer, it will just return to you the common log of 352 written exactly the same way. But if I then hit diamond enter, I get this, 2.54654. Okay? Which begs the question, where do we round? Well, let's take a look back over here at the original problem. Common log of 352. We see 3 significant digits here. This is an area in which logarithms differ slightly than our usual rules for standard deviations. When we are taking the log of a number, we note the number of significant digits in the argument, and then we express the answer not to the same number of significant digits, but to that number of digits after the decimal place. So this would be rounded to 0.5467. 0.547, because over here in the gray rectangle, you can see where I am rounding to, and the 5 means we go up. So we have 2.547, 3 digits to the right of the decimal. Rather than a total of 3 significant digits. All right, let's do another example. Let's find the common log of 25. We use the same sequence of keys, except for changing to the numbers 2 and 5 in the middle. And if you hit enter on my calculator, because I have it set for the exact answer, I get 2 times the log of 5. Now, why do you think that is? I'm going to leave that for you to explore. And I'm going to hit diamond enter on my calculator. And it tells me then that this is equal to 1.39794. And let's see. Let's take a look at our original problem. We have 2 significant digits. We're taking the common log of 25. So therefore, my answer must have 2 significant digits to the right of the decimal point. So if I mark that over here to the right, I'm going to be rounding to the hundredths place. That will become 1.40 because the 7 in the thousandths place will cause the 9 to round to 10, which causes the 3 to round up to 4. So our answer is the common log of 25 equals 1.40, with those two significant digits to the right of the decimal place, or rather decimal point. Let's do one more. Let's find the common log of 0.0640. And what does that equal? You might see that question posed in this way, that it is equal to some number y, and you are asked to find y. So you have to evaluate the log of this number, the common log. So diamond 7.0640 will get you there. The last 0 here is not actually needed by your calculator, but I think it's a good idea for you to put it in because it's a reminder that yes, all three of those, the 6, the 4, and the 0, are significant digits. Remember that the decimal is present, so you start counting from the Pacific Ocean, and as soon as you hit a non-zero number, you start counting and you go all the way to the end. So decimal is present, there's 1, 2, 3 significant digits. As you can see in our calculator box, we have 3 decimal places to the right of the decimal point. So that is actually our final answer there. And this video has too many layers on this slide, so I'm going to cut off this video here. You can see the rest of the discussion in the next video in Part B.